Okay, so welcome back. So at the end of lecture last time, I think I had started on, I hadn't done anything, I just stated the problem. So the example I wanted to do is let R be a triangular region in the xy plane between the graphs of y equals x and y equals 1 for x between 0 and 1. Let D be the solid region between the graphs of the surfaces z equals minus 2, so that's a plane at height z equals minus 2. And z equals 1 minus x squared, so it's like a parabolic sheet. And this is for all x, y, and r. So I went ahead and wrote out what this triple integral would be here. So I was asked to evaluate this triple integral over the region D described here of x plus 1 dv. Now, this was the problem statement, right? This x plus 1 didn't come from anywhere up here. This was just describing the region D I was integrating over. So the actual thing that I'm asked to do is evaluate this triple integral. Okay. And so I've went ahead and written out exactly what I need to do here to see how these limits of integrations go. So let's go to 2D here. In my xy plane, what is R, right? That this region D is defined over, so it's triangular region in the xy plane bounded by the graphs of y equals x and y equals 1. So y equals x, we know what that looks like. So there's y equals x. Y equals 1, I know what that looks like. And this is for x from 0 to 1. So there is my R. So I have this triangular region R below, and D is the solid region bounded between the graphs of z equals minus 2, that's a plane, 2 units down, right? And z equals 1 minus x squared, which is this weird parabolic sheet above R here, okay? All right, and so that's the D that I'm integrating over. So then this is the double integral over R, so that's why x here, y equals x, right, is the lower bound, viewing this as a vertically simple region. So this is the integral from 0 to 1, from x to 1, right, because my top function here is y equals 1, and z is bounded between the graphs of minus 2 and 1 minus x squared. So actually to see how this goes, right, I would maybe write out this region explicitly. This is kind of the thing that I always do here. So I have z bounded below by minus 2 and above by 1 minus x squared. And I have y. Viewing this as a vertically simple region, I could view this as a horizontally simple region and proceed in a similar way. So this is y is bounded below by y equals x and above by y equals 1, and x is bounded between 0 and 1, right? It's just my problem. That's just how it's stated here. Okay, so here's my region D, and then it makes it easy to write my limits of integration now. Okay, so let's do this triple integral. Okay, so let me copy that here. So I have the integral from 0 to 1, the integral from x to 1, the integral from minus 2 to 1 minus x squared of 1, it's x plus 1. I'll just write it as 1 plus x so I don't have to make any ugly marks here. dz, dy, dx. Okay, so I do my inner integral first, of course. So this is the integral from 0 to 1, the integral from x to 1. I'm integrating 1 plus x with respect to z, so there is no z here, so this is 1 plus x times z evaluated from minus 2 to 1 minus x squared dy dx, right? Okay. And so what do I get here? I get the integral from 0 to 1, the integral from x to 1 of, I have 1 plus x times 1 minus x squared minus 2, right? Okay, dy dx. Okay. And so let's expand this out all the way here so I can just do this as some big term by term thing. So I have the integral from 0 to 1, the integral from x to 1 of, let's see here, so where are my x cubed terms going to be? So I'm going to have x times minus x squared, so it's going to be minus x cubed. Okay, so that's the only x cubed term I'm getting. What what about my x squared term? So I just have this minus x squared times 1, and that's my only x squared terms too. So this is minus x squared. Okay, so now what about my x term? So I get a 1x from there, and then I get a plus 2x from there, and those are my only x terms. So that's plus 3x. And then lastly, my constant terms. So I have a 1 here. That goes with that 1 to give me 1, and then I have 1 times 2, so I'm going to have 2 plus 1, so I get 3 here, right? And that takes care of every possibility. So then I'm doing this integral with respect to y, then with respect to x. This has no y thing in it, so that's pretty nice. So this is the integral from 0 to 1. This integral is very easy to do. It's just that entire thing times y, right? Because there is no y term there. And that's evaluated from x to 1 dx. Okay. So that's not too bad here. This is just going to be the integral from 0 to 1 of plugging in 1 here. I just get that whole expression, so let's just write that. This is minus x cubed minus x squared plus 3 x plus 3 times 1 minus x, right, dx. So actually doing this expansion, I have 1 times this minus x times this. So multiplying 1 by this is easy. Multiplying minus x, I would get x to the 4th plus x cubed minus 3x squared minus 3x. Okay, and so what do I get? I get the integral from 0 to 1 of, so I'm going to get a plus x to the 4th. That's going to be the only term I get there. What gets subtracted off? I'm going to get a, so I'm going to get a 1 times minus x squared minus 3x squared. So that's minus 4x squared. The x cubed terms cancel because I'm going to get minus x cubed plus x cubed. So that cancels. The x terms also cancel because I'm going to get minus 3x plus 3x. And so the only thing that's left is the constant term, which is plus 3. Okay, dx. Almost done here. So now I do this integral with respect to x. I could just do this term by term here. So what's the integral of x to the 4th with respect to x? This is just 1/5 x to the 5th. What's the integral of minus 4x squared with respect to x? This is minus 4/3 x cubed. And the integral of 3 dx is, of course, 3x. And I'm doing this evaluation from 0 to 1. Plugging in 0 here, there's an x in every term, so I get 0 there. So then plugging in 1, what do I get? I just get 1/5 minus 4/3 plus 3. We can make that a little bit more palatable. Let's see here. If we get a common denominator of 15, I would get, so I would get 3/15 minus 20/15, so it's minus 17/15 plus 45/15, so that's 28/15. Right. All right. So, questions about that? Not blurry. Yeah, let me know if anything's blurry, of course. So if it's blurry for more than a couple people, please let me know if it's blurry for you. And you can't fix it by just reassigning your YouTube quality, because sometimes if you use like an auto quality thing, it will for whatever reason downscale it. Is the x to the 4th not negative? No, because it's minus x times minus x cubed. Yeah, so this is right, I think. I think this is all right. Okay. So, let's do more examples of this. So let me see here. What's another good? This is a really good example coming up. This is an example I always do. in this section because it's a really good example of getting you used to sometimes finding the R being not actually given it explicitly. So finding the R just from the solid region D. So let D be the solid region bounded by the portions of the circular paraboloids so Z is equal to, we'll say 3 minus x squared minus y squared, and Z is equal to minus 5 plus x squared plus y squared for x and y greater than or equal to 0. So this is in like the first and last octants, right? Okay, it's in the fourth of space that is facing you, right, in our normal orientation for how we're dealing with space. So notice that there's no R, right? So note my region R in the xy plane is not given explicitly anyway. It is in fact implicitly given. It is hiding here in this info. Okay, but let's say that you're given this region D. Evaluate. So what you are asked to do is to evaluate a triple integral. So we'll say the triple integral over this region D of y dv. Okay, so that's what I'm being asked to evaluate. Okay. So, first of all, what does this region D look like? So, these circular paraboloids are simple enough that you should have a nice catalog in your brain of what these things look like in similar objects. So, what do these look like? Well, if I draw my usual representation of space here, all right, so here's my x-axis, here's my y-axis, here's my z-axis. Then what about this circular paraboloid 3 minus x squared minus y squared? So you should have seen enough of these examples by now to know that what this thing is here I have height like 3, right? And this is my apex point for this thing. And then it opens downward, right? It's this downward opening paraboloid thing, right? So that's what it looks like. And of course it opens downward, forever. Okay, so if I look at cross sections of this, of course, my cross sections are circular. That's why it's a circular paraboloid, right? Okay, so this is my top. This is Z is equal to 3 minus x squared minus y squared. And then, if I want to look at my bottom paraboloid, I'm going to extend my axis down here. So my second paraboloid has its apex point, right, at minus 5, and it opens up. Right. And similarly, all of its cross sections are circles. Okay. Now, the region D, thus described, is this solid region I'm trying to outline here that is in this 1/4 of space facing me in this picture. Okay, that is somehow bounded above by the top paraboloid and circular paraboloid, and below by the bottom one, right? So there's a top and there's a bottom. They come together, okay, and they meet. Now, if I'm going to clean up this picture a little bit, what does this look like? There's my top paraboloid, and my bottom paraboloid. But the question is, all right, so you might see this. They meet, and so they meet somewhere. There's like this lip where they meet. Okay, and other than that, it's this weird thing that's like 1/4 of these circular paraboloids smudged together like this, okay? It's kind of hard for me to draw it like that, but you get the idea. Okay. Now, the region R that I'm seeking in my XY plane might look, let me use red in this picture, it might look something like this. Okay, it's the shadow. Now you might say, well, since this object is the way it is, since it actually covers the XY plane here in space, then it's not really the shadow. So then take this thing and move it up, right? Take this thing and don't do anything except translate it in the Z direction. So pick it up by the top, move it up as high as you need to go, right? So move it up and then shine flashlight, right? Straight down from the Z direction so that it's still that analog of the shadow cast on the XY plane. Okay, so how do I find this R? Some of you might have already said to yourself, well, I just see where these things intersect. Okay, some of you may already be thinking, well, they intersect at the XY plane. But is that true? You can actually tell that's not true just by looking at these things algebraically. How do you know that's not true? How do you know they don't actually intersect at the XY plane? I mean, they're not really symmetric paraboloids here, right? So the thing is that, you know, this one, correspondingly, this one has less of a height than this one, right? This is 3 units up on the z-axis. This is 5 units down. So there's no reason to expect those things are going to meet cleanly exactly in the xy plane, right? Yeah, so someone said in chat, they're not equidistant from the plane in the z-axis. Yeah, so they're not going to meet cleanly at the xy plane. In fact, what plane are they going to meet in? Well, how can I figure that out? Well, I can figure that out by doing the thing that you would want to do with this anyway. So you have 2 things and you're interested in the intersection of them. What do? You set them equal to each other, right? It's what you always do, right? When you're meshing algebra and geometry and you want to know something about intersection, you set them equal to each other. So I do that. I set them equal to each other. So if I set them equal to each other, I get 3 minus x squared minus y squared is equal to minus 5 plus x squared plus y squared. So let's do a little bit of algebraic manipulation here. Let's add 5 to both sides. So that's 8. 8 is equal to adding x squared and y squared to both sides. I get 2x squared plus 2y squared. I can divide both sides by 2, and what I get is 4 is equal to x squared plus y squared. Okay. Now, this tells me that what is this region of intersection here? This is giving you a hint, right? What kind of object is this? So these 2 things intersect, and what is their curve of intersection? Well, what curve is this? Someone knows. Yeah, circle radius 2 centered at the origin, right, in the xy plane. Okay, so, but this circle that they intersect in is not in the xy plane, right? So note this circle, so this circle of intersection is not in the xy plane. Well, where is it? How can I figure out? I can figure it out by plugging this relation into either one of these up here. Let's plug it into this one. All right, so z is equal to 3 minus x squared minus y squared. I could write that as minus x squared plus y squared, right? No harm in that. But x squared plus y squared for the circle of intersection is 4. Right? And so z is 3 minus 4. Z is equal to minus 1. What does that tell me? This circle of intersection occurs in the plane z equals minus 1. And so now I have a perfect geometric understanding of what this region D looks like. I have top paraboloid, I have bottom paraboloid. They come together in this lip. That lip of intersection is an arc of a circle of radius 2, and that lies in the plane z equals minus 1. So this lip of intersection occurs 1 unit below the xy plane. Okay. Now, how does this help us find R? Well, think of my flashlight analogy. My flashlight analogy is I'm either shining a flashlight from the positive z direction or from the negative z direction in a nice way. Again, if you don't like the fact that this thing passes through its own shadow here, don't worry about that. Just slide it up the z-axis and shine your flashlight again. The shadow that it casts, well, that shadow is going to be cast by that lip, right? What shadow is it going to cast? It is going to cast a shadow that exactly outlines a disk, a closed disk of radius 2. So this circle is the boundary of that shadow in the xy plane. Okay, and so even though this intersection curve did not occur in the xy plane, it occurred in the plane z equals minus 1, it is in fact going to be the boundary of our shadow anyway. If you don't believe that that's how it works, just take any 3D object you like and do exactly that kind of thing with it, right? So if I take like my drink container, right? If I shine flashlight on it, what's going to happen? So if I shine flashlight from directly below or directly above, it's basically going to cast a shadow from the outermost part of this, right? So for instance, this part of my region is going to get overshadowed, literally, right, by the part that's sticking further out. Okay, so this is an example of how visualization can help you, but notice that even here, this is a nice visual aid, but it's not actually required. You could, just by doing the algebra, you could see exactly how this goes. So yet again, even in a case like this, it's actually not needed. So if you are getting stuck on a lot of the visualization problems, just stop, right? Just stop even trying to visualize what's going on and just do the algebra, right? So that's my advice. Okay, and so how do I describe this region? So then my region R in the xy plane, of course, let's go back here. This is in my quarter of space that's facing me, and so what does that correspond to if I'm casting my shadow down to the xy plane? Well, it's this piece, right? So it's circle of radius 2, or a circular disk of radius 2, centered at the origin, but it's only for x and y greater than or equal to 0. Okay, so it's the first part. So how do I describe this? All right, well, let's describe this. It's both vertically and horizontally simple, but let's just describe it as a vertically simple region. So if I describe this as a vertically simple region, what's my top function here? So y is bounded below by the constant function 0, and it's bounded above by the function square root of what? 4 minus x squared, right? That's my upper semicircle function. And x is bounded from 0 to 2. All right, so there's my R. So then, totally describing my region D as required, I have Z bounded below by minus 5 plus x squared plus y squared, bounded above by 3 minus x squared minus y squared. I have y bounded below by 0 and above by square root of 4 minus x squared. And I have x bounded below by 0 and above by 2. Okay, so then my triple integral over the region D in question of y dv is the integral from 0 to 2, the integral from 0 to square root of 4 minus x squared, the integral from minus 5 plus x squared plus y squared to 3 minus x squared minus y squared of y dz dy dx. Okay. So I do my inner z integral first. There is no z here, so this is simple. I have the integral from 0 to 2, the integral from 0 to root 4 minus x squared of yz evaluated from minus 5 plus x squared plus y squared to 3 minus x squared minus y squared dy dx. Okay, so let me think here for a second. So I can do this subtraction quickly. So this would be 3 minus x squared minus y squared minus 5 minus x squared minus y squared. So I would get minus 2x squared minus 2y squared, and then I would have an 8 here. So this would be the integral from 0 to 2, the integral from 0 to square root of 4 minus x squared of y times 8 minus 2x squared minus 2y squared dy dx. Okay. All right. So let's see here. What next? Let's be careful here, looking ahead a little bit. There's an easy way I could group these that is going to make my life easier. So let's do it like this. Let's say this is the integral from 0 to 2, the integral from 0 to square root of 4 minus x squared. Let's write this as 2 times 4 minus x squared times y minus 2/3 times y cubed. Okay. Dy dx. Okay, that looks better. All right, so I just rewrote this to make this slightly nicer. Okay, so let me keep that. Let's keep that expression on the page here. Okay, so let's do this term by term here. I integrate with respect to y. This is the integral from 0 to 2. Here, the integral of this thing with respect to y would be y squared over 2, so that 2 gets left out, and so this is 4 minus x squared times y squared minus 2/3 times 1/4 y to the 4th evaluated from 0 to root 4 minus x squared dx. Okay. All right. So what do I get here? So both of these have a y in them, so evaluating at 0, I get 0. Plugging in square root of 4 minus x squared, what do I get? Well, so let's see here. This is the integral from 0 to 2. I get 0 and plug in 0. Plugging in square root of 4 minus x squared here, I would get 4 minus x squared. Root 4 minus x squared squared is 4 minus x squared. Minus 2 over 12 or 1 over 6. All right, so this is 1/6 times the root 4 minus x squared to the 4th dx. And so what do I get here? This is the integral from 0 to 2 of 4 minus x squared squared. This is also 4 minus x squared squared. So this is 1 times 4 minus x squared squared minus 1/6 4 minus x squared squared. So this is 5/6 times 4 minus x squared squared dx. So this is 5/6 times the integral from 0 to 2. I can just expand this if I want to. So what do I get here? This is 16 minus 8 x squared plus x to the 4th. All right, dx. And so this is 5/6 times, I can integrate this term by term here. So this is 16x minus 8/3 x cubed plus 1/5 x to the 5th. Evaluated from 0 to 2. So evaluating at 0 gives me 0. And so really I just have the term where I plug in 2 here. So I have 5/6 times 16 times 2 is 32 minus 2 cubed is 8. So this is 64/3 plus 2 to the 5th is 32. So that's plus 32/5. Okay, so then this is, let's get a common denominator here of 15. Okay, so if I get a common denominator of 15 here, I got 5/6 times, well, do I really want to do that, or do I just want to leave it like that? I could just leave it like that. That's fine. This is fine. We'll stop here. No point getting bogged down in the arithmetic. If you're doing this on an exam and you get to this point, you're good. Okay, all things have been evaluated. No integral left to do. This is it. Okay. All right. So, questions about that? All right, so I have one more kind of conceptual thing I wanted to talk about with triple integrals before moving on to the next topic, which is still triple integrals, but it's something a little different. So, volume as a triple integral. I know that you haven't been, intimately connected with the notion of a double integral for a long time. But it turns out that when you were doing double integrals, you were actually doing triple integrals. How? Well, let D be a region in space, so a solid region. So let D be a solid region in space, defined as in this section. Then the volume of D can be computed as volume is triple integral over D of 1 dV. Where have you seen something similar to that? All right, so compare with what we knew about area of R, right? So the area of R could be written as the double integral over R of 1 dA. So this is very, very similar in form here. Okay. Let's see. Question, when I rewrote the equation, where did the 2/3 in front of the y cubed come from? Well, let me go back here. Let's see here. Here. Oh, it's when I did the integral here. So I did the integral of, let's see here. That shouldn't have been there. This should be just a -2. So this should just be a -2 here. Because I hadn't done the integral yet. So that's what I was doing. Now, did I? Yeah. Okay. So that would slightly change the form. So basically, this would be a 2, and so in the actual So this would also be a 2. And so rather than there being a 5/6 here, you'd have 1 minus 1/2 is what this should be. So this should be a 1/2 here. So it would change this to be exactly 1/2 here. Yeah. So now it should be right. And that's also, this is actually an easier thing to find. So this is, let's see. So this would be, 16 minus 32 thirds plus 16 fifths, which is 128 15ths. Yeah, so now it's right. So thank you for saying that. Okay. So the volume here, seen as a triple integral. Note that if D is seen as usual as the region bounded above and below by two functions, so we'll say the lower function's big F sub 1 of xy to big F sub 2 of xy for xy in some region R, then this volume is my triple integral over D of 1 dV, but really this is the double integral over R of the integral from big F sub 1 of xy to big F sub 2 of xy of 1 dz dA, right? Oh, but hey, what is this, right? After I do this evaluation, this is just the double integral over R of big F sub 2 of xy minus big F sub 1 of xy dA. And so you obtain an integral formula for computing the volume between two graphs of two variables in the exact same way in Calc 1 that you computed the area between the graphs of two functions using technically a double integral, but it reduced to a single integral, right? So it's exactly analogous in this way. Okay, and now that you've seen how triple integrals work, you could do this for any number of integrals, right? So you could do this for quadruple integrals if you wanted to, right? So you could be integrating over some four-dimensional hyperregion, right? We'll call it H, right? And you have an H here. Let's just write it out, right? So H is some hyperregion, right? So H is a region in R4, right? So it's four-dimensional. And we'll say that it's simple in that I can view H as the region between, so H is, we'll call a point in H, we'll label X, Y, Z, W, right? Why not? Okay. And so W is bounded between two functions of three variables. We'll call them little h sub 1 of x, y, z and little h sub 2 of x, y, z. And then z is bounded between two functions of two variables, right? F sub 1 of xy and big F sub 2 of xy. And this is on a simple or a vertically simple region. So y is bounded between the graphs of two functions. We'll say g sub 1 of x and g sub 2 of x. And x is on some closed interval, right, a to b. So if I wanted to define the quadruple integral over h of some function f of x, y, z, w, right, d hypervolume, right? Then, well, this would be the integral from a to b, the integral from g sub 1 of x to g sub 2 of x, the integral from big F sub 1 of xy to big F sub 2 of xy, the integral from little h sub 1 of xyz to little h sub 2 of xyz of f of xyz w dw dz, dy, dx, right? That's how it would be. Okay. Now, it turns out that past Calc 3, we don't really care that much about evaluating integrals in this form. But even if we did, and even so, it's not that we don't talk about integrating in R4 and higher. Of course, we do. In fact, you'll do this for general N. So rather than considering a region in R4, you'll talk about a general region omega that's contained in Rn. But when we do this, we don't do quadruple integrals, because if say n is like 50, right? I'm not going to be stupid and write 50 integral signs here. What I will do is I will do this. I'll do this. I'll say the integral over omega. If omega is in Rn, then this is technically, right, this is it's in integrals like that, but I don't care. I'm just going to write it like this. Okay, so we move to symbols that look like this instead, so that we don't have to spend, half the paper writing out integral signs or anything. Okay. Also, you deal with more of the conceptual properties of expressions like this rather than actually getting some real number spit out of this thing. Okay, so that's where this heads. Okay, so that is all I wanted to say about the basic triple integrals now. So then the idea is the following. Some triple integrals are over regions that, while simple enough, are kind of nasty in rectangular coordinates. In rectangular coordinates for space. When we say rectangular, we mean the usual, right? X, Y, Z here. So just like for double integrals, it turns out that some of the regions we want to integrate over and some of the things that we want to integrate would be much nicer in different coordinates. Okay. Now, you already had the notion of polar coordinates coming from Calc 2 or wherever you'd seen them. But for coordinates in space, you might not have ever seen an alternate coordinate system. You might only know X, Y, and Z, right? And so, whenever you're trying to innovate, right, it's nice to not get too far ahead of yourself. It's nice to do kind of the stupidest thing possible. And so, moving from what we did in the plane to go into polar coordinates, right, from rectangular coordinates in the plane to polar coordinates, in space, what do we want to do? What if we just take polar coordinates and we add a z? Right? Well, that's exactly what we're going to do, and that's called cylindrical coordinates. Okay. So cylindrical coordinates. What is the idea here? The idea is take polar coordinates in the xy plane and toss in z. And so we go from coordinates x, y, z, describing a point in space, and we go to coordinates r, theta, z. The transformations are exactly the same. Z goes to z. You don't need to change anything there. X squared plus y squared is r squared. And x is r cosine theta. Y is r sine theta. Right. Here, I know that by taking y and dividing it by x, I get that tan theta is equal to y. Right, tan theta is y over x. Okay, so here's my transformations in both directions. What does this actually look like? So how to describe cylindrical coordinates. Okay, so here's x, here's y, here's z. Let's take a generic point, right, x, y, z. I want to see how this point is actually the same as the point r theta z. What's the idea? Well, the idea is that if I project this point down to the xy plane, then we're at the point x, y, 0, right? Okay. In the xy plane, there is a distance from this projected point to the origin in the xy plane. That distance is r. Okay. This segment measures out an angle measured from the positive x-axis. That angle is theta. And so, to see the point xyz as r theta z, the height is exactly the same. All you do is you look at where you are in the xy plane, right? That is some distance to the origin. That's r. That's your first coordinate. Okay. This angle measured from the positive x-axis, just like in polar coordinates, is your theta. Okay. And so this is r theta z. Nicholas, that's something we do later. That's another type of coordinate. So that's actually what we're going to do right after this. So that's called spherical coordinates. So Nicholas in chat mentioned, do we use the azimuthal angle for z? That is an angle measured from the positive z-axis to give us three coordinates, r, theta, and phi. We are going to do that. But that comes later. So that's a different coordinate system. Okay, so cylindrical coordinates is in a way simpler than that, but there's some things that are much nicer in spherical coordinates than in either rectangular or cylindrical coordinates. Okay, and so this is cylindrical coordinates. Now, how does this help me? Right, so how does this help? So just like for in the case of polar coordinates in the plane, the idea was that this made certain expressions a lot easier. So big question is, how does this help? Right. And the answer is some things are a lot easier to describe in cylindrical coordinates. Oh, gee. So I'm going to ask a total brain teaser here. What things do you think are easier to describe in cylindrical coordinates than rectangular coordinates? Okay, this is like a 900 IQ question, right? What thing is easier to describe in cylindrical coordinates than in rectangular coordinates? I know. I have faith. I have faith in all of you here. Right. Unless you really think that mathematicians have specifically misnamed this type of coordinates. Yes, a cylinder, right? So hopefully cylindrical coordinates are good at describing cylinders, right? That would be the hope. If that's not the case, then something has gone very, very wrong here. So there's a nice table. This is in your book, but if I'm talking about the surface type here, and I want to see what this looks like in rectangular versus cylindrical coordinates. So the surface itself is a cylinder. What does a cylinder look like in rectangular coordinates? Well, x squared plus y squared is equal to a squared. Now, before I go any further, you're going to look at that and you say, wait, that's not the equation for a cylinder. That's the equation for a circle, right? But remember, this is an equation in space, right? So let's add a little asterisk here, right? So the asterisk says this equation is in space, i.e., what I'm really saying here is there's words said before you write down this equation, and those words are the collection of points x, y, z in space such that x squared plus y squared is equal to a squared, right? So you have to throw that in, because if you don't, then technically this is a circle, right? If only x and y exist, this is the equation of a circle. But sitting in space, you're looking for the collection of all points x, y, z. Satisfying this, that is a cylinder. It's a cylinder determined by that circle. So there's a circle in the xy plane of radius a, centered at the origin. This is that cylinder, right, determined by that circle. But in cylindrical coordinates, what is that? So in cylindrical coordinates, remember, x squared plus y squared is equal to r squared. And so if x squared plus y squared is equal to a squared, then this is r is equal to a. So in cylindrical coordinates, I can describe a cylinder by specifying a radius. So that's nice, right? That's a lot nicer than in rectangular coordinates, right? So if you have a region that is involved with intersecting cylinders or something like that, this is going to be a lot easier to describe in cylindrical coordinates. Okay, a sphere is not great to describe in cylindrical coordinates. It's better than rectangular, but it's not great, and we're going to have spherical coordinates that do a better job of this. So a sphere is x squared plus y squared plus z squared is equal to a squared. So in cylindrical coordinates, like I said, this is a little bit nicer, but it's not great. This is r squared plus z squared is equal to a squared. So that's okay. Like, that's fine. But like I said, we're going to have better coordinates for dealing with that. We could talk about a double circular cone. So double circular cone. In cylindrical coordinates. Again, the cone is going to be better described in spherical coordinates, but it's okay. I'm going to go ahead and write this out. So x squared plus y squared is equal to a squared z squared. So that's it in rectangular coordinates. It's just r is equal to az in cylindrical coordinates. Okay. And it's called a double cone because, of course, it looks like this. And these are called the naps of the cone. So there's the upper nap and the lower nap. So that's what the double circular cone looks like. And then there's like circular paraboloid. Which is not so bad. So this is x squared plus y squared is equal to az. Right? So this becomes r squared is equal to az. Right, so there's your circular paraboloid and cylindrical coordinates. Now, it's probably not surprising to you that by far the most common use of cylindrical coordinates for us is going to be the case that you're dealing with a region that involves a cylinder or intersecting cylinders or something like that. Okay, so at the beginning of class next time, I will state the main integration fact about cylindrical coordinates, and then we'll be done with them. I'll do a couple of examples, then we'll be done. We'll move on to spherical coordinates. Okay, so I think that's that. So I will see you all on Wednesday.